Today we are doing 18.3, and it is similar right triangles and the exploration. And this is helping us understand how we use sine, cosine, and tangent, those trigonometric functions, to find sides and angles. So it's a preview of an upcoming attraction. So the first thing we're going to do is look at solving a right triangle. Each triangle, as you see, has three parts. So you have three angles and three sides. So you see an angle here. Let's see. We have an angle. We can call that a B for beta. Whoa. All right, so that's a beta. These are all Greek letters that you see, lowercase letters. This is an alpha. All right, and then this is a 90-degree angle. So what we're looking at are similar triangles that have 90-degree angles. And so again, remember, each triangle has the three angles and the three sides. And when what's coming up is when we have an angle here, we'll call that's a 23-degree angle. And dang, I hate it when it does that. I have to guess where to put it. Anyway, there's your 23-degree angle. Then you have a side that's 4.5. So you see this side here that's 4.5. And then we have two other sides of the triangle with just those two bits of information and using trig. What's coming up is we can use actually a trig function such as tangent, and we can do tangent of 23 degrees is equal to, equal sign went all over the place, opposite, which is b over the adjacent side, 4.5. So what you see is tangent 23, that's just a number. It's an irrational number, but it's still just a number, and you can actually find that in your calculator. You can hit tangent 23 and hit enter, and it's a ratio of two sides of b to 4.5, and it's 4.4245. So we have two numbers that are equal to each other. We have 0.4245 is equal to b over 4.5. So when that's the case, we can just multiply both sides by 4.5, and we've got what b is equal to. So 0.45 times tangent 23, I'm just going to do tangent 23, is, 4.5 times tangent 23. And you can do that in the calculator, and you can get that side is going to be, this side is 1.9, all right, units. So pretty awesome that we can actually find any side knowing two things, an angle and a side. We can find any of the other two sides. So we can do the same one. We just have to pick which of the trig functions to use. So again, and this one, if I say I want to know angle B, I'm not sure what angle B is, but I want to find out what angle that is. They use this in any type of navigation. If you're flying an airplane and you want to hit a certain point, you have to, we're not going to be dealing in centimeters, but if you were dealing with miles, you would know at what angle you need to take your aircraft and how long, at what magnitude, how far the distance that it needs to go in order to make sure that you land properly at an airport. So it's pretty awesome. So if we want to know this angle, we have this 5 centimeter side, and it's opposite to the angle, and we have this 10 centimeter side that's the hypotenuse. And so we can use a sine inverse function to come up with the ratio 5 to 10, and we can find out what that angle is. In fact, I can use my calculator right now, sine 5 divide 10, and that's going to be a 30-degree angle right there. So it's really crazy that we can use these trig functions. That's what we're going to learn. This is kind of an understanding why it works lesson that eventually we'll use the pre-understanding to show you why the trig functions are useful and how they can help us find sides and angles and triangles. So here we have a 28-degree angle. We have this side that's opposite the angle that's 12. We have this side that's adjacent to the angle that's x, and that would be a tangent function. Tangent 28 is equal to 12 over x. So we can solve for x and come up with that actual side measurement that we've labeled x. So pretty cool stuff. That's what's coming. That's a preview of what's coming. The first thing we need to do is label the sides. And the sides are always going to be a ratio of one side to another side. So that's why you know that fractions or what the result of that is. A ratio is a fraction. So if I get 1 over 2, I can simplify that, and it would actually equal the same thing as 3 over 6. And it can be simplified. So the crazy thing is with right triangles and similar triangles, you end up with the same exact ratio, because no matter how big or small, as long as they're similar triangles, when you take two sides and find the ratio of sides, then it's going to be a number that's simplified, or a specific number that's always going to be the same for each of the ratios of each of the sides of the triangle. So the first thing you need to do is, if we know this angle, and we know the ratio, which luckily our calculators have them all pre-programmed into them, and you don't have to do like your grandparents did when they were in math and look at tables and the ratios that are specific to those angles. And we know that's true because of similar triangles. At least you can use the calculator to come up with these ratios that are always the same because of the similarity of proportional sides in similar triangles. So if we're going to label the sides, you notice that this side, these green, is the hypotenuse. It's always the hypotenuse, no matter what. And then when we see this angle theta here, then we have the two legs, and the two legs toggle between opposite and adjacent depending on where the angle is. So opposite means it's opposite the angle. Adjacent means it's adjacent to the angle. That side's adjacent to the angle. Adjacent sides to the angle run right into the angle. So if you go directly, just take your eyes directly opposite that angle, then you're going to have this side that's the opposite side. Okay, happens every time. If you look at the angle that just runs right into that, or the side that runs right into that angle, we call that the adjacent side. So you have a hypotenuse that remains the hypotenuse no matter which of the two angles. Oh, and by the way, we're not going to ever check the 90-degree angle. We always just let that go. Eventually, when we deal with unit circles in Math 3, you'll look at that opposite. You look at the 90-degree angle and the sine and cosine of those. But for now, we're dealing with specific triangles that are made, and the 90-degree angle we don't worry about, but the other two, we call them acute angles because they add to 90, so they must be less than 90. Then we look at those angles and which sides relate to them. Opposite is always opposite the angle. Adjacent is always adjacent to the angle and runs right into it. All right? Now, just for your information, because you guys are honors, you can handle this. Say this was alpha. That angle was alpha. Notice that the hypotenuse remains the hypotenuse, but if I go directly opposite that angle, this side is now our opposite side, and this side runs right into alpha, so it's the adjacent side. So see how it depends, the opposite and adjacent sides depend on which angle we're referencing. So we have to look at the angle to know which one is opposite that angle and which one is adjacent or running into that angle. And then again, the hypotenuse remains the hypotenuse. So if we are labeling sides, then adjacent, hypotenuse, and opposite are the three sides. We only have to label three, and we have a very specific measurements to give. Now, that's alpha. We're looking at alpha for these three, and this little alpha looks like that. Alpha. So I like to label the hypotenuse first because that one's always a hypotenuse. Then I go from the angle and I look directly opposite to get my opposite side. And then whatever side runs right into that angle is the adjacent side. So adjacent and opposite are the legs. They form that right angle. And they form the right angle and become opposite and adjacent depending on which of the angles it is. All right, so now here we have alpha on example 2. So again, this is the hypotenuse. And then directly opposite, I always label that next, and then running right into it is the adjacent side. All right, so here we have 2 to choose from. Again, we're looking at only alpha according to our directions here. So if that's alpha, then here's our hypotenuse. It's directly opposite the 90-degree angle, always, longest side, hypotenuse. And then from alpha, if I carry my eye right across here, I have the opposite side. And then running right into the angle, alpha is the adjacent side. All right, so we can move on. Oh, I did not mean to do that. I don't know how that happened, but Well, all right, now we're looking in reference to angle beta, B. So you see there's the beta right here. That's the angle. Again, this is hypotenuse. Hypotenuse runs into beta also, but the hypotenuse is specifically across the 90-degree angle, and it's the longest side, so it's just the hypotenuse no matter what. Opposite beta is that side, and adjacent to beta running right into beta is that side. All right, so here's beta on example 5. We have the hypotenuse. Want to label it. Directly opposite is this side, and then running right into it is the adjacent side. Okay, now a lot of times with these, I'll just do O, A, and H. So anyway, H on example 6 is right there. Across from beta is the opposite leg, and running right into beta is the adjacent leg. Okay, now that's going to be important when we talk about some other things, but just note that that's what we do first is label, and that's how we label. It's always O, A, and H depending on the hypotenuse is the hypotenuse, but O and H or O and A are dependent specifically on the angle in reference. All right, triangle similarity. Now we're going to look at these ratios according to triangle similarity. Remember that we can prove triangles are similar by angle similarity, side similarity, and side angle side similarity. Those are our 3 proofs that allow us, theorems that allow us to show that triangles are similar. If they're similar, remember that their angles are congruent and their sides are proportional. So we're going to just remember that from the last unit. That was very important. Are these similar, and if so, state why. So if you look at example 7, we have N and B that are congruent. They have an arc saying so. And C and M are double arced each, so that means they're congruent. And therefore, we have the 2 congruent angles. So, yep, they are similar by angle similarity. All right, the next group, example 8 of triangles, we have angles that are vertical that are congruent. So for sure, those are congruent. But we have to determine whether or not the sides are proportional. They have to be proportional in order for them to be similar. So I always like to take one triangle and go small to big on the top, because I have to go small to small, big to big, and it's just easier that way. And then 56 and 84 are the other triangles sides in order from small to big. So I need to check 24 divide 56, and it is actually 0.429. And we need to check if that is equal to 35 divide 84, and that is 0.417, and they are not equal. So nope, they are not similar. Okay, so for example 9, we have one angle marked, K and R congruent by a single arc. We also know vertical angles, when lines cross and create vertical angles, they're congruent. So yep, this is congruent by, or not congruent, similar by angle similarity. All right, not similar for angle 8 or example 8, but the other 2 examples, 7 and 9, are indeed similar. All right, so this next part, I'm down to my 15 minutes, so we're gonna hit this example next. And so just go ahead and move on to the next video, part 2.